Hi everyone, today I'm going to be presenting this paper called LAM, Leveraging Language Prompts for Multi-Person Pose Estimation, published in IROS 23. So basic overview of the method is this paper first proposes uh, using CLIP to estimate multi-person pose. So the challenges in multi-person pose estimation is in crowded scenes, it's difficult to estimate the pose of humans because of the occlusions and also the instance separation. Like in multi-person pose estimation scenario, there can be multiple humans at this same spot, and at those positions, estimating pose can be difficult. And in this paper, they have showed uh, if they use language supervision, this challenge this challenge can be remedied a little bit or more or less. And also in this architecture, they introduced an architecture called LAMP, where they use prompt-based inference strategy that uses language model representation to enhance understanding and overcome option challenges like we talked about before. And it also performs better than other existing methods, which uses single stage or top-down or bottom-up strategies. Usually they do in pose estimation field. So a bit background about the method is nowadays people are using a language to facilitate downstream tasks like pose estimation, segmentation, and all. So to do those tasks, most of the time what that we use is CLIP, which is trained on 400 million image text pairs to understand modality relationships. So in CLIP, they have an encoder, which is for text, and they use that encoder to encode the text prompts, uh, and the text would be similar or more associated to the field they're going to be applied it on. Uh, and they use the clip encoder, and you somehow like manipulate the image encoder to get them uh, uh, to, to do the downstream tasks for their purpose. So, we can see a few examples like a depth clip or a clamp where they have shown uh, how to use clip to do downstream tasks like depth estimation or pose estimation for animals. So the overview of the method looks like this. So here it looks a bit more complicated. I will go into much more details later. So to explain briefly what they do in this method is they have two sections or two stages in this method. In first stage, they align the text prompts to the each instance of the image. So let's say there are two instances here. You can see like there is one human, there is another human, there are two humans. In first stage, they align the text prompts to each instance of the image, and later they use those aligned instance features to estimate the pose using another contrastive learning technique of similar to CLIP, where they use the text encoder to encode another pairs of text and image and estimate the pose in the latest stage. So let's go into the details. In the first part, here, like I said before, they do align the instance to the text. So let's first look at the image encoder. So they have made some change, which is like in CLIP, we know they use VIP-based method to get the image embeddings. Here they have made some change to align it to the instance features. So let's see how do they do it. So in the first stage, they extract the multi-scale image features from the backbone, like here, the extracting features from the backbone. And in this case, in this paper, they have used HMF to get the multi-scale features from the image. And then they concatenate the features and generate global image features app here. And after getting the app, we in that paper to do operation called spatial attention, where they use an instance aware mask (MI), which is computed based on the location of each instance's center point. So each instance's center point is this, like for this human, the center point is this. So they calculate a mask based on the center point of each instance. And later they calibrate the spatial instance feature for each instance. The FS means the spatial attention features, but FSI means the feature for individual instance. So this for this instance, that would be one feature, for that instance, that would be another feature. So to recalibrate the spatial features, they do this operation. So this is the global features and this is the individual mask, and they are multiplied both together to get the individual spatial features. And later stage in a channel attention part, they get the channel feature map for each instance by performing element-wise multiplication of the output of this channel attention module to align the instance feature with the global features. And later they combine both spatial attention features and the channel attention feature like FS and FC and FS using these equations. So they concatenate both and they use a convolution layer to combine, put together after concatenating, and use a ReLU to fuse the features, both FS and FC features, for which are then used for a further processing for later stage. So let's see how do they generate the text in text in. They use different attribute to create the text prompts, such as location, depth, and inclusion. So they use a prompt like this here, like it's shown here, a dash person on the dash. So they first divide the images into 3x3 sections, and then they have three blanks. So it's for this blank. So for these blanks, it's for like how far or close the instance is. So like if in each section, so there are 3x3 sections. In each section, what they do is they take the bounding box of each instance, and if the bounding box is small in each section, then they say if the instance is farther away in the image. So like think of it in like, don't think of it in sections, like in different sections, think of it in the image. So if the bounding box is small, so typically what it means is the person in the image is farther away, normal, like let's say here, this bounding box would be smaller than this bounding box. So the depth of this instance would be higher comparatively to the depth of this instance. That's what they estimate from the bounding box. And next stage for the occlusion section, they estimate occlusion based on the number of visible key points. So they check for each instance how many key points are visible. If the number of key points are not visible up until certain threshold, they take that instance is occluded, and if that's not the case, they take it as not occluded. And then after, oh, another thing. So since they have divided it to like 3 by 3 sections, there are 6 sections. So for the last section, they just put it like top left, top right, bottom or whatever, depending on the uh, position of each upon each section. So later, after constructing the prompt itself, they uh, send the prompt to the clips text encoder, and then they get the embeddings here. And in this work, they have frozen the text encoder. Text encoder of clip did not train the text encoder. They just trained the image encoder for both cases, for instance prompts and the later stage, the join prompt. They don't train the text encoder here. So later, after getting the embeddings from text encoder, um, they use a self-attention module to um, to project the text embeddings to the image embedding. So their way of encoding image is different than the usual clips image encoder. So to project their image embeddings to the clip image embedding space, or other way around, so the text embedding space to their image embedding space, they use a self-attention layer to project those features. And to align instance and the text, they use the dot product of the image, each instance feature, and the the prompt for each instance, and later they do the contrastive learning, contrastive loss to align those features. So later, let's look at the next stage, join prompt. There are they do two things in join prompt. First, they align the features to the key points. So there's key point alignment, and later they also align the pixel feature of the image to the prompt, which they say improve the accuracy. So to map the features from the instance features we have gotten previously, and they again send it to another self-attention layer to um, to to turn it into an embedding, and later they use the text again, the embedding of text from here, from the joint, like nose, the left shoulder, and all these prompts, they get text embeddings, and they also transfer or the convert the instance embedding to this same image, same dimension or same embedding space of text embedding here by using another self-attention layer. And to generate text, they use like the level of the each key points, like nose, left shoulder, right shoulder, like it's shown here. This is the number of key points for humans for a particular data set. So for different data set, the number of joint levels will be different. Then you calculate the sign similarity between uh, the disembedding here, and also the instance embedding there, previously gotten there. They calculate the sign similarity, and they try to maximize in this direction by using compressive learning, which they say align the features of key points more with the text embeddings and hence improve the accuracy. Yes, they use the compressive learning. It's basically said in this slide. So next part is the pixel level alignment. So they use the same features as gotten before, the instance features. and they later what they do is is then instead of doing sign similarity, they use this equation to find the similarity between pixels and uh, and the key and these joint labels, uh, and then also perform contrastive loss. So added to contrastive loss, they do one thing. They for this part, supervision of this part, they use like heat map to align the features furthermore to the pixels and the text embeddings. So these are the loss functions they use. Like I haven't written the loss, the map portion of it there, because it's mostly universal. So they are using previous losses there in this method. So first, they use contrastive loss for the images, and they also use the focal loss for heat map regression. They also estimate the heat map for each instance, and for um, prompt loss, they use the mean squared error between the textual embeddings and image features and applies cross entropy loss for key points level aligned. So this is basically for contrastive loss, and MSC loss for pixel level supervision for the heat map portions. They form MSC based loss to match the heat map generated by the previous step and align those heat maps to the pixel in the latest step. So this is the result they show. Like here, they compared it with three kinds of methods, like top-down methods, bottom-up methods, and single-stage methods. They show if they use language-based supervision, their method outperforms all the existing methods in purpose datasets. And later, they also show in Mosaic dataset, like before, compared to all three methods, if they use language-based supervision, the method outperforms all the other methods. And here they also show the impact of each component of the model. So as they were adding more and more modules into their model, it generally increased the performance of the model. And there are some qualitative results where they show if they use language supervision, the method does better when it's occluded. Like here, if the human is occluded by another human, and so the previous methods is failed. But if they use language supervision, here they perform better than the existing methods. So that was it for me. If you have any question, please let me know.